Okay, so we just got done talking about potential and kinetic energy, and now we're going to be talking about mechanical energy and applying it to work. So mechanical energy is essentially energy that is due to an object's position and or its motion. So looking at mechanical energy, we're going to be looking at both the potential energy of an object, which is the energy due to position, and the kinetic energy of an object, which is the object in motion. So we can look at a couple of examples. A moving car possesses mechanical energy due to its motion. A book at rest on top of a shelf possesses mechanical energy because of its vertical position and it's elevated. And then a moving baseball possesses mechanical energy because it has both kinetic energy because it's moving and vertical position because it is above the ground. So the total amount of mechanical energy is the sum of potential and kinetic energy, meaning in order to find an object's mechanical energy, the total mechanical energy, that's going to be just the potential energy plus kinetic energy. So we have a image here that we're going to be looking at. At top, we have a skier, and we see that the kinetic energy is 0 joules, so they're not moving at this point, but he has 50 joules of potential energy. So if we were to look at these two numbers, in order to get the total mechanical energy, we would add those up. So the total mechanical energy at this point is 50,000 joules. Sorry, I'm struggling with that 5. Well, you get it. Okay, so the total mechanical energy is 50,000 joules, and that is going to be true the entire time this object is moving throughout this path. So again, as you go down a hill, that potential energy is going to basically turn into kinetic. So we are now gaining some velocity, so we're going to be gaining some kinetic energy. We see that we've lost potential energy. We've lost 20 joules of potential energy, and that potential energy is now kinetic energy. So if you add those two up, the total mechanical energy is still that 50,000 joules. I guess I can't write 5s on the screen. So again, total mechanical energy, looking at the object's potential plus kinetic as it's going. And we can look at the object at the bottom of the hill. It has now 15 joules of potential energy. So because it is less elevated, it's going to have less potential energy. But now the skier is going to be at a very high velocity. So they're moving fast, so they're going to have a lot of kinetic energy. And again, if you add those two numbers together, you're going to get that 50,000. Let me try that again. Nope, still not going to get that 5. Okay. 50,000 joules at that point as well. And you can continue to look at the skier at both these points. They're all going to be 50,000 joules of total mechanical energy. So that energy is getting transformed into kinetic and then back into potential. Now we're going to look at how energy deals with work and forces. So there are a couple types of forces we can look at. There's internal forces, which would be considered gravitational spring forces, and then there's external forces, such as applied, normal, frictional, and air resistance. And we categorize these depending on how it changes the object's total mechanical energy. An external force is not going to change the total mechanical energy. It's going to remain constant. If an external force comes into the picture, comes into play, and causes the object to either lose or gain energy, we consider that a external force, and that is going to change the total mechanical energy. And then we can look at positive and negative work and how it relates to energy. So if we have work being done, it can either be positive or negative work. an external force in the opposite direction of the object, we're going to consider that negative work, and it's going to cause that object to lose mechanical energy. If we have an external force in the same direction, so we're going to gain energy in this point. We do positive work, we give that object more energy, so that again, that mechanical energy is going to increase. So if we're doing negative work, we are going to lose mechanical energy. If we're doing positive work, we're going to gain mechanical energy. Like everything in physics, there's going to be a formula to go along with it. It's going to be the total mechanical energy initially. So again, when I look at this, there's an I here that stands for the initial total mechanical energy plus work exerted, and that's going to equal the total mechanical energy final. So whether this work is negative, positive, it's going to affect this total mechanical energy final. And then we're going to actually look into a more in-depth formula. So we have our total mechanical energy initially, which essentially is our kinetic energy initially plus our potential energy initially. And we know our work formula is force times distance times the cosine. And that's going to be the kinetic energy final plus potential energy final. So we have an example we're going to do together. I'm going to do this on it's hard to write on the computer, obviously. So I'm going to do it on a piece of paper over here. So when we set up these total mechanical energy questions, we're going to be doing multiple steps. So the first thing we want to look at, we're going to be looking at, again, this total mechanical energy initially plus work equals the total mechanical energy final. And we're going to break this formula up into what we need to find. So this is KE, so kinetic energy initially, plus potential energy initially, plus work we know as force times distance times cosine. And that's going to equal PE final plus PE initial. So we broke that into what we want to find. And we can break that down even farther with the formulas that we have for potential and kinetic energy, but I'm not going to do that because it makes it for a long formula. But I'm just going to draw our potential energy formula over here, which is mass times gravity times height, and our kinetic energy formula, which is mass times velocity squared over 2. So we're going to be looking at these formulas again and bringing back our work formula as well. So this is the formulas we're going to be using. And let's look at this practice problem. It says, at the end of a roller coaster ride, the 5,000 kilogram train is slowed from a speed of 30 meters per second to a speed of 10 meters per second over a distance of 23 meters. Determine the force required to slow the train of the cars. So whenever we're looking at these problems, we're going to be setting it up the exact same way every time. So we need our total mechanical energy initially, meaning we need our kinetic energy initially, and we need our potential energy initially. So looking back at the question, initially, how fast was this car going? And it says it was going 30 meters per second. So that's going to be our velocity. And our mass is 5,000. So again, we're going to be looking at our kinetic energy formula to fill this in. The velocity initially was 30. And we're going to divide that by 2. So we're going to plug that into the calculator to get our initial kinetic energy. So 30 squared times 5,000 divided by 2. So 2,250,000 joules of kinetic energy initially. And then we need to look at potential energy. It does not give us the height, or it does not tell us the roller coaster is elevated. So it does not give us a height. We just assume that the potential energy is 0. So anything times 0 is 0. This roller coaster has 0 joules of potential energy initially. So we found this part of the formula. Now we need to look at the work part. So our work part is, again, force times distance times cosine. So our force is what we want to find. We're determining the force that was needed to make this occur. So F is going to be left as F. And then it gives us a distance of 23 meters. And then you want to ask yourself, is this positive work or is this negative work applied to the roller coaster? And the answer is negative work. It's going to cause the roller coasters to slow down. So we need that cosine 180, which essentially makes your answer negative. So 23 times negative 1 will be F times negative 23 meters. So we have now solved for work. And now we're going to move on to our total mechanical energy final. We need our kinetic energy finally, and then our potential energy final. So at the end, we need to see if this roller coaster is still moving. Does it still have velocity? And the answer is yes. It's 10 meters per second. So that mass does not change. It's still 5,000. It's now 10 meters per second. So we're going to square that and divide by 2. So I'm going to plug that into the calculator. So now it's 250,000 joules of kinetic energy. And now when you look at potential energy, the cart is not elevated. It does not give us the height it was elevated. So we assume it is 0 joules of potential. So we have found our potential and kinetic energy initially. We found our work, and then we found our kinetic energy final and our potential energy final. So now we're going to plug it into this formula. So our total mechanical energy will be these two added together, and that is going to be the 2,250,000 joules plus our work, which is just going to be F times negative 23, and that's going to be our total mechanical energy final, which again is potential plus kinetic. So add those two numbers together to get 250,000. So again, we added our potential and kinetic initial to get our total mechanical energy initially. We found our work. We're leaving F as F because that's what we're finding. And it is negative work, so it made this number negative. And then we're finding our total mechanical energy final by adding these two together. So this is the whole formula that we're going to be using, and we're solving for F. So the first thing you want to do is subtract your total mechanical energy initially to either side. And you'll be left with $2 million, and bring down the force times negative 23. In order to get F by itself, you divide by negative 23. Oh, and this is going to be a negative 2. So this is going to make it a positive force. So divide those two numbers together,